So this first one just asks us to find the sum of the sequence. So remember, when we are adding fractions, we need to make sure that we have common denominators. So we see that we have 1/9. So we're going to have to turn 1/3 into ninths. Okay, so that's going to be to multiply by 3/3. So this is going to be 3/9. And then when we add the tops. So we're going to do 4. Okay, so add the tops, 3 plus 1 over 9. Okay, keep the bottoms the same. So 1/3 plus 1/9 is 4/9. So now when we take a look at this next one, and if I kind of erase this here, we'll see that these tops just changed to 2's. So I could actually divide a 2 out here, and let me change colors so we can see the difference. Okay, I could actually divide a 2 out of here, and when I take a 2 out, this becomes 1/3, and this becomes 1/9. And then we already know what 1/3 plus 1/9 is. Okay, we just figured that out in the last one. It's 4/9. So now I could just double that. Okay, and 2 times 4/9 is then going to give me 8/9. So remember, you only double the top. Okay, then the next one. So now we have 1/3, 1/9, and 1/27. So now we're going to want to get a common denominator of 27. So we're going to multiply this by 9/9. So 3 times 9 is 27. 1 times 9 is 9. We're going to multiply these by 3 because 9 times 3 is 27. And 1 times 3 is 3. So now we'll be able to add these tops. So 9 plus 3 is 12, plus 1 is 13 over 27. Now we're going to see that same thing happen down here where we just have 2's. So we can divide a 2 out. This will give me 1/3 plus 1/9 plus 1/27 when I divide that 2 out. So this is going to just be 2 times 13/27 because we already multiplied that. So now we're just going to double this. So 2 times 13 is 26 over 27. Because remember, 2 is like 2 over 1, and you're just multiplying tops times tops. So 2 times 13 is 26, and 1 times 27 is 27. All right, then this next one, okay, now we go to 1/81st. Okay, so now all of these can become 81. So we'll multiply 27 times 3, which is 81, and 1 times 3, which is 3. 9 times 9 is 81, so then we would do 1 times 9. And 3 times 27 is 81, so then we do 1 times 27. So now we're going to add these tops, and I'm going to do 27 plus 3 is 30. 9 plus 1 is 10, so 30 plus 10 is 40 over 81. Now this next one, okay, again, just has those same numbers, but with a 2 on top. So let's divide a 2 out, and we'll get 1/3 plus 1/9 plus 1/27 plus 1/81st. Okay, so we'll just be able to do 2 times our previous answer, which was what these all added to, was 40 over 81. And when I multiply 2 times that, I get 80 over 81. Number 2, Priya's walking down a long hallway. She walks halfway and then stops. Then she walks half the remaining distance and stops again. She continues to stop every time she goes half the remaining distance. So what fraction of the hallway is left when Priya has started and stopped 2 times? Okay, so let's take a look at like a full, I'm just going to put a full distance here. Okay, so here's the full hallway, let's say. So then Priya is going to walk halfway. Okay, so she's going to get here, which is halfway. Then she's going to walk another halfway. Okay, so she's going to walk half of this, and half of a half is a fourth. So now she's gone a fourth of this distance. Okay, so now she's gone another fourth of the way. But so this number here, if we think about this, okay, is 3/4. Okay, so going halfway left would be 3/4. So this says, what fraction of the hallway will Priya have covered? Okay, so she's covered 3/4. Because essentially, okay, when you talk about this, she's got a fourth of the distance left because she's got half of a half. Okay, so she's got 1/4 left. Okay, so she's covered 3/4. So if we take a look at this, what fraction of the hallway will she have left if she starts and stops 4 times? Okay, so here she's halfway. So she's got half of it left. So then she's going to stop another half of the way. So now the remaining distance is 1/4. Then she's going to stop again, and half of a fourth is an eighth. So now this amount is 1/8, and then she's going to do it again. So now she has 1/16. So this is how much she has remaining. So she has 1/16 remaining. So that means she's covered 15/16 of the hallway. Okay, that's how far she's gone. And then will she ever reach the end of the hallway repeatedly starting and stopping at half the distance? So if you keep having, so now she's going to have 1/32nd, and then she's going to have 1/64th left, and then she's going to have 1/128th left. Okay, and this would just continue on, and this bottom number would just keep getting larger and larger, so you'd have a smaller and smaller portion left. So technically, she never gets there. But now this number gets to be so small that it doesn't matter. Okay, so at some point, the distance won't actually matter. She'll get to the end. Okay, but eventually the distance remaining is too small to matter. Number 3, a geometric sequence starts with these two terms. So it's geometric. So we know that we're multiplying here or dividing. Explain how you would calculate the 100th term. So in this case, to go from 10 to 5, we're multiplying by a half or dividing by 2. So we're going to have to take 10 times 1/2 99 times. Because remember, we took it times 1 time to get the second term, 2 times to get the third term, 3 times to get the fourth term. So then to get the 100th term, we would do it 99 times. Number 4, here's the graph of a sequence. Define R recursively using function notation. So we need to come up with the first term. Okay, and we can see that these are counting by ones because 1, 2, 3, 4, 5. So our first term is 1. Okay, so R of 1 equals 1. And then we want a recursive formula. So we want to define it based on the previous term. So R sub n is equal to R sub n minus 1. Now we see that it's curving and looking like exponential. So this is going to be geometric. So we're multiplying by something each time. So our first term is at 1. Our second term is at a height of 2. Our third term is at a height of 4. Our fourth term is at a height of 8. So you can see we're multiplying by 2. So then we're just going to multiply by 2. And this is going to be for any term greater than or equal to 2. Number 5, an unfolded piece of paper has a thickness of 0.05. Complete the table with a thickness of a piece of paper after it's folded in half n times. So if we fold it in half once, it's got 2 thicknesses, right? So it's got, So we're just going to add or double its thickness. Okay, so we're just going to multiply this by 2. So we'll get to 0.1. Now when we fold these in half, it's going to double its thickness again to be at 0.2. And then we'll fold it in half again, and it'll double its thickness again to be at 0.4. So now let's define this for the nth term. Okay, so we had this 0 term. So we know that the nth term is going to be the initial term, so the one they gave us at 0.05. And then we're going to multiply this by the growth factor to the n. Okay, and our growth factor is this timesing by 2. So we're going to take the initial thickness and we're going to double it a certain number of times. So 1 time, 2 times, 3 times, 4 times, however many times is going to go there. So what's a reasonable domain? And so we talked about this in a previous one, but you can really only fold a piece of paper up to 7 times. Any more than that, and it's too thick and too hard to fold in half again. Number 6, again, has this paper being 0.5 inches thick, and then we're going to complete the table after it's been folded. So this is the exact same table. Okay, so it's just going to double it each time. So we're going to get 0.1, 0.2, and 0.4. Now, does it make sense for us to have t of 0.5? So does it make sense to have a 0.5 in this n column? And no, because you can't do a 1/2 fold. You can't half fold the paper. You either fold it fully or you don't fold it at all. Number 7, an arithmetic sequence starts at an arithmetic sequence A starts at 84 and then 77. Define this recursively. So for this one, we see that it's arithmetic and it's going down 7. So recursively, we would say what the first term is 84. Then we would say that any subsequent terms are going to be equal to the previous term minus 7 for every term greater than or equal to 2. So now when we define it for the nth term, okay, this one, we have the first term. So a sub n is going to equal the first term minus that common difference n minus 1 time. Okay, because we subtracted it once to get the second term, twice to get the third term, 3 times to get the fourth term, 5 times to get the fifth term. So we would subtract this common difference 1 less than the term we're finding. So if we're finding the 17th term, we're going to subtract it 16 times. The 100th term, we're going to subtract it 99 times. All right, then number 8, here's a pattern of growing rectangles. Describe how the rectangle grows from step 0 to step 2. Okay, so here we have a 1 by 3. Here we have a 2 by 1, 2, 3, 4, 5, 6. Here we have a 3 by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the width appears to be growing by 1. So the width looks like it's plus 1. Okay, the height looks like it's plus 3 each time. And then write an equation for a sequence so that S sub n equals the number of squares in step n. So when we look at this, there's 3 squares here. There's 2 times 6 or 12 squares here. There's 3 times 9 or 27 squares here. So if you look at these, we can see that these are all similar, okay, from bringing back some of geometry. So if we look at this first one as the original, okay, it looks like this one doubles, right? It doubled the dimensions. And then when we go to this one from the first one, it tripled the dimensions. Okay, those are like your scale factors. So if we look at this first one is 3. The second one is double or has a scale factor of 2. So the second one's area is going to be 2 squared times bigger, the scale factor squared. The third one, the scale factor is 3. So that one's going to be the first area times the scale factor squared again. So now the scale factor is 3. And if you wanted to think of this one, okay, its scale factor is 1. So then if we generalize that for the nth term, okay, so if we went to the nth quadrilateral, we would multiply by n. Okay, so the area is going to be multiplied by n squared. So that original area, okay, so we'll call this S sub n will equal the original area times the term number squared. And then is S geometric, arithmetic, or neither? And this is neither because it's multiplying by the term number squared, not by a specific number squared. We're not multiplying by 2 to the n, or 3 times 3 times 3 times 3 times 4 times 4 times 4 times 5 times 5 times 5. Okay, we're multiplying by the term number squared. So this is going to be neither.